So the last thing that we were doing was we were learning how to write electronic configuration of small atoms. So I told you that electrons are filled around shells, and hypothetically you can have a lot of shells, but basically every atom has a very fixed number of electrons, so you don't need that many shells. Shells are simply regions around the nucleus where the electron is actually kept. The electrons are attracted to the positive nucleus in the center, and these are the shells. And as you go further and further away from the nucleus, the size of the shells increases and you can accommodate more electrons. So the first shell is the tiniest. It can only accommodate 2 electrons. The second can accommodate 8. Then you have 18, then you have 32, then you have 50. And I also told you about the fact that most of the elements that are stable, that are usually found around you, the everyday elements, they are small atoms and they don't have a lot of electrons. So the first thing that we did was we learned how to write the electronic configuration of small atoms, which are the ones having proton numbers less than 20. And just one second, I need a periodic table. So proton number less than 20. So up till calcium, these are all your small atoms. Carbon, nitrogen, oxygen, we are basically made out of carbon. Almost all living organisms are made out of carbon. The atmosphere is nitrogen. So most of these elements are the ones that you usually find around yourself. These are small atoms. Uh, and for small atoms, I told you, you don't need to know that many shells because you're going to run out of electrons anyways. So for small atoms, what you do is uh, that you just simply write 288, which means that you fill the first one with 2 electrons, the second one with 8 electrons, and so on. So you don't need that many shells for small atoms. So for chlorine, if it's 17 electrons, so it's 2, 8, and 7. If it's nitrogen, it only has 7 electrons, so that's 2 and 5. And I told you to write the electronic configuration of the first 20 elements. I'm going to post this on the Google Classroom. I think that it's not there right now. So I'm just going to do one more example. Let's pick aluminium and calcium, and I'm going to quickly try and write the electronic configuration of let's say aluminium is 27 and 13. Remember this, I told you don't look at the position, just look at this. The small number is the number of protons, 13 protons, and if it is a neutral element, then the number of electrons are going to be exactly the same. And the number of neutrons is the difference, 27 minus 13, so that's going to be 14, I think. So I'm just going to quickly write the electronic configuration of this atom. So that's your nucleus. That's one of the shells, the second shell, and the third shell. So how are 13 electrons going to be arranged? So just write 2 in the first one, and they're going to be 8 in the second one. And you already and you run out of electrons. There's only 3 electrons that would occupy the third shell. So I'm going to add these over here. One second. So that's your nucleus. The nucleus has protons and neutrons. And here are your shells. 2 in the first one, 8 in the second one. And you've got 3 in the last one. Now, that's one way of writing electronic configurations. That's one way of writing electronic configurations, but there are shortcuts as well. The shortcut is that if you look at the periodic table, I'm not going to move towards big atoms at the moment. We're going to do those at the end. The first thing is, by just looking at the periodic table, you can guess the electronic configuration of an atom. You can either calculate the electrons and write the electronic configuration, or the other thing that you could do is that the periodic table, you can guess some of the things about the electronic configuration by simply looking at the periodic table. So I'm going to just quickly tell you a brief short introduction of how elements are arranged in a periodic table. So elements are arranged in groups and periods. So there's this. But let me take a snapshot. I'm just going to post this over here. 1 second. Which is this one. So here's my periodic table, and you've got groups. The columns are the groups. You've got group one. This one is group two. So I mean they're already numbered on the periodic table. Then similarly you have group three, four, five, six, seven, and zero. Uh, and there are various ways. Some periodic tables have numbered them differently, but that's how your groups are going to be numbered. So it's group five, group six, and you've got group seven, and the last one, the noble one. It's sometimes referred to as group eight, or like over here, it's referred to as group zero. So the vertical ones are your groups. So let me just mark one of them. So this one is all the elements in, I mean, these are elements in group one. Similarly, these are elements that are part of group two and so on. And then you've got periods as well. Now periods are the horizontal rows. Like the first one, I mean, this is your first period. It only has two elements. So that's period number one. You get the one marked in green. This is going to be period number two. Similarly, this would be period number three. So you've got groups, and you've got these horizontal rows that are your periods. So this one is period one. This one is period number two, and so on. So you've got, as you can see over here, there are almost seven periods. I mean, the last elements are actually, they're so radioactive that you don't actually, they're very, very rare. So these elements are usually just created in the lab, and they're very, very rare. You can't really, smaller atoms are more abundant. I say, anyways, what do you do with groups? And I mean, that's the basic structure of a periodic table. The other thing that you should know is that elements are arranged according to the proton number. I mean, you've got hydrogen, that's the first one. Uh, Hydrogen doesn't have a place. Remember, hydrogen is the element that doesn't really have a group. Uh, so that's hydrogen. Then you have helium, that's two. Then it's three, four, five, and six, and seven, eight. So elements are arranged according to their proton numbers. And they're arranged consecutively. There's no missing gap. Like for every proton number, there's an element. Like there's 80, 81, 82, 83, and so on. So there are no gaps. Elements are arranged according to. So they are not arranged according to the number of electrons. They're not arranged according to the number of neutrons, but they're arranged according to the number of protons. Another important thing about elements is that each element is also defined according to its proton number. So according to their proton number. So for example, if you have carbon, no matter what the atom is, like if you have carbon, I mean carbon could be 6 and 12. I mean, this is one type of carbon. There could be several different types of carbon. So this is one type of carbon that's given in the periodic table. This is the one that's more abundant. So carbon is 6 and 12. So that means all the carbon atoms in the universe, they would be identified by this proton number, which is 6. Uh, if the proton number changes, the element changes. But there could be other types of carbon as well. There could be carbon which would be 13. There could be a carbon which would be uh, 14 as well. But as long as they are carbons, their proton numbers are fixed. All carbons in the universe would have 6 protons. They can have different number of electrons, they can have different number of neutrons, but the number of protons is going to be exactly the same. So all carbon atoms will always have 6 protons. And the reason elements are identified according to their proton numbers is that basically an atom is defined by its nucleus. For example, carbon has 6 protons and it has 6 neutrons. So, so the so the nucleus of a carbon atom has a positive charge of +6. I mean, the neutron basically has no charge. So the neutron isn't really playing any role. It's not attracting anything. It's not repelling anything. So the neutron is just most of the time it's completely irrelevant. It has nothing to do. It doesn't attract anything. It doesn't repel anything. So it's not doing anything in a chemical reaction. So why is the nucleus positive? Because it has 6 protons, and which is why a neutral atom would have 6 electrons as well. So for example, here's a neutral atom and it has 6 electrons. So 2 in the first one, and there would be 4 in the second one. Now the number of electrons can also be lost and they can be gained. So every atom is defined by its nucleus, not the neutrons. The neutrons can go up and down. We don't really care because the neutrons aren't really doing anything. The positive charge of the nucleus depends on the protons. So the property of the atom is basically defined by the center, by the nucleus. The electrons can be lost. Some atom can steal these electrons. Some atom can give it electrons. So the number of electrons around it can change. They can always change. Uh, and It can lose all of its electrons. It can gain a bunch of electrons. So the electrons are always changing. So just remember this, elements are always defined according to proton numbers. And if you're being asked what is the definition of an element, so I'm going to write the definition of an element, that it's basically a substance that contains atoms of the same type. Of the same type, uh, having the same proton numbers or atomic number. You can also call it the atomic number, same proton number or atomic number. So when we say carbon, when we refer to carbon, we're basically talking about a substance that contains atoms where all the atoms are carbon atoms. And how do you know they're all carbon atoms? Because all of them are going to have 6 protons. The number of electrons can change, the number of neutrons can change. We don't really care. As long as it has 6 protons, you're going to call it carbon. If the number of protons changes, the name of the element also changes and its properties would change. Its chemical and physical properties would change, because if the center part has a different positive charge, the element would behave kind of differently. So the properties would also change. So is this point clear? You clear? Saad, is this clear? Ashita, Amna, is this clear? Turhan, any question? I couldn't hear you. Is this clear?
Yes.
Okay. So just it's a simple point. Just remember, uh, when you say that something is chlorine, that means it is bound to contain 17 protons. The top part can be different. It could be 35, it could be 37, it could be 38. It could have different number of electrons. It could have different number of neutrons. But the if you're calling it chlorine, the proton numbers would be fixed. It's always going to be 17 protons. I say, anyways, uh, the next part is, okay, I was talking about the pure table. That pure table is the elements are arranged according to the number of protons, and sometimes you're asked if there are any missing elements. There are no missing elements because there are no gaps. Wherever you see there's an element with 21, there's an element with 22, there's an element with 23. So there are no missing gaps anywhere. The next thing I'm going to talk about is what information do you get from groups, or if I tell you that an element is in group two, what does that mean? So if an element is in group two, so group number, that tells you the number of electrons in the outer shell, or which is known as the valence shell. So group number, if something is in group one, group number is equal to the number of electrons in the outer shell. In the outer shell, also known as the valence shell. So, for example, so you will get a very vital piece of information by just looking at the group number. You don't have to draw the atom always. For example, aluminium again. If you look at aluminium, you just need to open the pure table and you can see that aluminium is in group three. It's in the third group. So that directly indicates that aluminium has three valence electrons. So it has three electrons in its outer shell. And we just drew the aluminium atom, which was before this. So you can clearly see that it has three valence electrons. So you don't have to draw. I mean, in that case, the pure table will help you. I mean, that's why it's arranged according to that. That you don't have to draw the atom always. If you want information about the electronic configuration of an atom, you just look at the pure table and you'll get that information. If an element is in group 7, for example, bromine is in group 7, that means it has 7 electrons in its valence shell. If an element is in group 4, like carbon, without even figuring out how many protons, neutrons, and electrons it has, without any calculation, if it has 4 written over here, that means it's got 4 electrons in its valence shell. And we drew the electronic configuration of carbon, which is over here. It did have 4 electrons in the outer shell. So that is the information that you get from the group number. And what vital information about electronic configuration do you get from the period number? So when we are going to do chemical bonding, remember you don't have time to write the electronic configuration or draw the structure of the atom every time. So you'll be using group numbers and period numbers to figure out what the electronic configuration is. So what does the period number tell you? It specifically tells you the total number of shells. The total number of shells that are present in an atom. Uh, so we know that carbon had two shells. It had a total of 6 electrons. So we can get that information by just looking at carbon. So carbon is, I mean, this is the first row. The first row is kind of empty because the first shell can only have 2 electrons. So there are not a lot of atoms there. But look at carbon. Carbon is in the second row. It's in the second row. I mean, the horizontal thing is called a row. ठीक है, the so going this way, that's your row. So carbon is in period 2, which means that it's got just 2 shells. and we did actually find that it did actually have two shells. Similarly, if you look at aluminium, aluminium is kind of over here. So by just looking at that's first row, second row, it's in the third row. So that means aluminium is going to have three shells. And you can also confirm that we did draw aluminium somewhere, and you can confirm that it has three shells exactly. So is this point clear as well? Clearer?
Okay.
Okay, so just remember, you can write the electronic configuration, or you can just look at the periodic table, and that would give you a lot of information about the electronic configuration. Now what we're going to do is we're going to try and learn how to write the electronic configuration of big atoms. So this is going to be different, and this doesn't really come very frequently because big atoms, I told you, are kind of not that abundant. Most of the time, the electronic configurations that you'll be asked would be about small atoms. But there would be some questions where you will be asked about this electronic configurations of big atoms. Now, you don't have time to draw that many shells, so we're not going to draw the shells. We're just going to list how many electrons would they be present in the first shell, or the second, or the third. Now, let's say I want to figure out the electronic configuration of bromine. So, what is a big atom? I mean, that's the first thing. A big atom is one where the number of protons are greater than 20. So let's keep 20 as the mark. If the number of protons is greater than 20, we're going to classify them as big atoms. So for example, over here, calcium is 20. So let's call that a big atom. Not above 20, sorry. Scandium would be considered a big atom, and beyond that, anything that's above 20, that's a big atom. So how do we write the electronic configuration? So bromine has 35 electrons, right? It's 35 and 80. It's given in the periodic table. It's where's bromine? Bromine is over here. So I'm going to first thing is I can't really figure out the electronic configuration straight away. What I'm going to do is I'm going to take help from the group number and the period number. If you look at bromine, it's going to have 1, 2, 3, and 4 shells. And it's in group 7. Bromine is in group 7. So I'm getting two informations about bromine from the periodic table, that it's in period 4, and secondly it's also in group 7. So these two pieces of information are given in the periodic table. Now period 4 means that it has 4 shells, and group 7 means that the outer shell or the valence shell has the valence shell has 7 electrons. So these are the two very important information. So what I'm going to do is I know that it has 4 shells. It's in period 4. So I can either draw those 4 shells. Let's try and draw them first. So here's shell number 1, there's shell number 2. So shell number 3 and shell number 4. अच्छा, ये सारे ना 4, these are your 4 shells. And so how would I fill them up with electrons? So I'm going to first write the electronic configuration like these are my 4 shells. The first shell always has 2 electrons, and the second shell always has 8 electrons. So what you can do is, instead of actually filling the first shells, what you can do is you can start off with the last shell. You know that the valence shell has 7 electrons. So fill the valence shell with with 7 electrons. That's the outermost or the last shell. So it has 7 electrons. How many electrons do we have in total? In total, you've got 35 electrons. So 7 are present in the outermost shell. So that means you're left with 28 electrons. So you're going to fill up the rest of the 28 electrons in these shells. And you're going to fill them up in the same way. The first shell is going to have 2 electrons. The second one is going to have 8 electrons. So that's 10. And now you're left with so out of 28, if you remove 2 and 8, that's still 18 electrons to go. So the third shell will have a total of 18 electrons. And this is exactly what we studied. We studied that early on, we did study that the third shell can have a maximum of 18 electrons. We were following the 288 method because the first 20 elements, they did not have enough electrons. So the shells were not getting filled up. So for the first 20 elements, we were just using the 288 method. But now for bigger atoms, remember that the third shell can have a maximum of 18 electrons. So this is what you're going to do. You're going to, if you have a big atom, you look at the big atom, look at in what period it is. If it's in period 4, that means it's got 4 shells. So 1, 2, 3, 4 shells. And if it's in group 7, that means the last one is going to have a maximum of 7 electrons. And so out of 35, the last one has 7 electrons. So you're left with 28. So you fill up, start filling over here, 2 electrons, 8 electrons, and the remaining electrons go over here. So is this clear? Turhan, is this clear? Amna, Ashida, Saneem, is this clear?
Yeah.
Salama, is this clear? Saad?
Yes.
Okay, so just important thing, this only applies to big atoms. So we're going to pick another big atom. Let's pick, let's pick rubidium. So rubidium has 37 electrons now. So let's try and write the electronic configuration of, this one I'm talking about, rubidium 37. So it's Rb, and it's 37. That means it has a total of 37 electrons. Right now, I'm not concerned about the number of protons or the number of neutrons. I'm just looking at the electronic configuration of the shells. So 37 electrons. What do I need from the periodic table? I need to know which group and which period this rubidium is in. So if you look over here, rubidium is in group 1. So that means it has 1 valence electrons. The other information is in what period is rubidium. Rubidium is in period number 5 because this is the first period, the empty one, which has 2 elements. That's the first period. Then this is the second period, then third, then fourth, and it's in the 5th period. So rubidium over here is in group 1 and it's in period number 5. Group 1 means that it has 1 electron, 1 valence electron. So the outermost shell is going to have 1 valence electron. And since it's in group 5, in period 5, that means it has a total of 5 shells. So it has a total of 5 shells. So we did not actually fill this up. Let me fill this up as well. It's 2 electrons. Then there are 8 electrons. You wouldn't be asked to draw this because it's time consuming, but you will be asked about this thing to state the electronic configuration. Then you had 18, so that's 2, 4, 6, 8, 10, 12, and 14, and 16, and 18. And the last one had 7 electrons, so that's 1, 2, 3, so that's 6 and 7. So this is how a rubidium atom would actually look like. That's the nucleus in the center. sorry, a bromine atom would look like. So moving back to rubidium. So I've got rubidium over here, and one valence electron. It's got five shells. So I'm going to draw the. I'm not going to draw the atom. Five shells is too many. I'm just going to write these five shells over here, and I'm going to tell you which shell is going to have how many electrons. So what's the first thing? Can you even tell me what do I write over here in the last shell?
One.
Okay, so that means it's got one valence electron, so that's one. Okay, the last one. That's one electron. So out of 37, if I remove one electron, so I'm left with 36. So the rest of the shells are going to have a total of 36 electrons. So I'm going to start with the first one. That's two electrons. Then the second has a maximum of 8 electrons. The third one will have a maximum of how many electrons? How many electrons are we left with?
18.
So can you even do the math as well? Like 18 plus 10, that's 28, right? So I need 36 electrons. So 18 plus 8 plus 2, so that's 28. So there are 8 more electrons to go. So there would be 8 electrons over here. Is this clear?
Sir, I just have a question.
Yes.
Sir, is it all right that the fourth shell isn't completely occupied?
What's the question? Is it?
Sir, is it all right if the fourth shell isn't completely occupied? Because there's a fifth shell as well.
You're talking about this one.
Please, sir.
This one is always, I mean, you always fill this one first. I mean, the reason we're starting with the last one is that we got that information that by looking at the group number, we figured out the last one is going to have one electron. I mean, it's always the first that's always filled first.
No, as in, like, sir, you know the fourth shell?
Yeah.
Is it all right if
I'd
it's
say this
not
one.
completely full?
Tika, that's a good question. So the point is, the problem is that electrons actually don't get filled. Like you're filling the first two electrons, they fill up in the last first. I mean, they always fill up in the first shell. Like the nucleus in the center is positive, right? Okay, so that's a positive nucleus. So the electrons are going to be attracted and they'll fill this one up. The second one also gets filled completely. The problem comes after the third shell because you got so many electrons that the electrons don't actually fill in a particular order. Like if you see over here, you would notice that the fourth shell is actually not completely full, and there are electrons in the shell after that as well. So the thing is that once you move towards bigger shells, the electrons kind of filling electrons kind of becomes complicated. So it's all right. I mean, it actually happens this way that the fourth shell is not complete, but the fifth shell has started filling up. Amna, is this clear?
Yes, sir.
So it's something normal because the problem that happens is, I mean, this happens with the third shell as well. Like after 8 electrons, I mean, there's so many electrons that the electrons actually prefer the outer empty spaces. Do you get the point?
Yes, sir.
So, so the thing that you just have to keep it simple. The thing that you just have to remember is uh, group number. That's the number of valence electrons, the last one. Period number. That's the number of shells that you have to fill up. Now you have already filled the last one, so fill the remaining in the remaining shells. 36 electrons start off over here. 2 electrons, 8 electrons, 18 electrons, so whatever the capacity of the shell is, and there would be 8 over here. So you're going to get questions like this. They would I mean, you do usually get questions on big atoms, and it's going to be like this. It's actually going to be like this. I mean, there would be missing numbers over here, and you'd be asked to fill those numbers in. Similarly for bromine, I mean, they won't ask you to draw this because it's going to be just too time consuming. So try and write the electronic configuration of. So I'm just going to post this in the group in the classroom as well. Uh, Let me just post the homework over here. Just 1 second. I said, does anyone else have any questions? Salama, is this clear? Ashida, is this clear? ठीक है बाकी
Yes.
तुरहान
Yes.
अच्छा चलिए. Okay, just 1 second. I'm just posting question. You're supposed to write the electronic configuration and draw the atoms. Uh, so you were supposed to draw the draw structure of the atom with the whole shells, and you were supposed to write protons, neutrons, and electrons of first 20 elements. So that was number one. Number two is you were supposed to state, don't draw, just state, like just put dashes and write the electronic configuration. So do it for, we did it for bromine, and we did it for, I mean, do it for gallium. So let's do it for gallium. Okay, just find wherever gallium is. Okay, just state the electronic configuration. Similarly, do this for try doing this for iodine as well. So these two. So just so I'm just going to label this. So 1 second. As this one is done, just posting this right now. Send this by tomorrow. I'm going to send you something else as well for tomorrow as well. So make sure your previous work is all done. Okay, I'll be posting results for this and sending this on the group.